Today, I want to talk about the tools you will encounter in software engineering. More specifically, I will approach the discussion of tools from a very low level, progressing into higher and higher levels of abstraction of the software engineering role. Finally, I will wrap up the video by giving you some advice regarding tools in your first job as a software engineer. This is the 5th video in the series on applied software engineering, but the 4th one that talks about the various tools and processes that are widely used across the software engineering industry today. This video is intended for an audience that is interested in finding out more about the software engineering profession, but has little experience in the industry. Alright, I think that's all that you need to know before we begin, so let's get to it. Let's begin today's discussion by talking about the best known task in software engineering, writing code. But before we can get to that, what even is the logical process behind writing code? The general process behind writing code is first doing some research on how to solve the problem at hand, then modifying text files containing the code that needs modification to solve the problem, followed by executing the code to verify that the problem is solved, and the process concluded by getting the code changes approved and merged into some repository. This 4-step process, however, is not a pipeline, but rather a repeated cycle that looks something like this. For example, you will probably not get the code right on the first attempt, so you will go back to research whatever new problem you hit, make new modifications, and go through the cycle again. What is the purpose of this discussion? Well, there are many different tools involved at each step of the cycle that are worth discussing in this part of the video, and we will begin the discussion with the simplest step, modifying the text files containing the code. At this part of the cycle, you will encounter many tools of varying complexity, anything from simple text editors to more specialized source code editors, and all the way to integrated developer environments. A text editor is usually an extremely simple program that is mostly intended for really small changes, with examples such as Vim, Emacs, Nano, and Notepad. When it comes to source code editors, these are more specialized to making changes in code files, so they come with more functionality, bells, and whistles. Examples of source code editors are Visual Studio Code, Sublime, Atom, and Notepad++. The common features of these editors are syntax highlighting, autocomplete, version control integration, and rudimentary code search. Lastly, when it comes to integrated development environments, or IDEs, these are heavyweight programs that allow you to do everything within them without having to really leave for almost any reason. Usually, these will have serious code search engine integration, static analysis tools, more feature-rich debuggers, and even simulation environments in some cases. Some examples of IDEs are CLion, Visual Studio, PyCharm, Eclipse, and Android Studio. As you can tell, as the code editors get more involved, they simply integrate better with other steps of the code writing process. Therefore, let's move on to the 3rd step in the process and discuss the tools involved in executing and verifying that the code you wrote actually works. The absolute first tool that must be mentioned is either the compiler or the interpreter that the language you wrote the code in uses. This is what enables you to actually execute the code that you wrote, and each language may have more than one compiler or interpreter that works for it. For example, for C++, there are GCC, Clang, and MSVC compilers. For Python, there are the CPython, PyPy, Jython, and other interpreters. I think there are multiple tools that can run code written in a more popular language, but even some of the more esoteric languages may have multiple implementations. The next set of tools worth discussing here are debuggers. Each programming language that is actually used will come with some tools that help with debugging defective code. Such debuggers allow you to execute code in a special environment where you can pause code wherever you want, inspect the state of the entire system during execution, and even modify it. These tools are incredibly useful, as they allow you to find the root cause of the introduced defects faster than you may have otherwise. Common examples of debuggers are GDB for Common Systems Languages, PDB for Python, and I will also bundle Valgrind here as well, even though it's a different type of debugger to what I discussed so far. The last set of tools that I would like to mention for this step of the software development cycle are static analyzers. These tools allow you to catch defects and security vulnerabilities in code without actually executing the code itself. Some examples of such tools are the Clang Static Analyzer and SonarQube. Next, let's go back to the problem and solution research step in the software development process. I left this for later because we are now starting to get a bit further away from the task of actually writing code, but this step contains a lot of very useful tools. The first tool that is important to mention here is Google, or any search engine for that matter. The thing is, there is an insane number of resources out there to help you with figuring out how to solve the problems, and Google allows you to search for documentation, blog posts, videos, tutorials, and so much more. However, your company may have internal documentation, so you will encounter search engines that index internal docs like Yippee or Google Cloud Search. Speaking of things you likely will find on Google, you will find forums that allow users to ask questions and get answers. Such forums include Stack Overflow, mailing lists, Reddit, and discourse forums, with Stack Overflow being absolutely the most popular one. Some companies also host such forums internally with Google Groups and Discourse, so look out for these too. The last set of tools that I would like to bring up for this part of the software development cycle are code search tools. When working for a large company, the code repositories may grow so large that the simple code search tools such as grep or whatever is bundled in your IDE may not actually be able to index the codebase in a reasonable amount of time. In cases like that, you will likely encounter dedicated code search tools that sometimes run on their own servers and keep indexing code so you can search it quickly and effectively. Some examples of code search tools are OpenGrok, Google's Code Search, Facebook's Big Grep, and GitHub's Code Search. Alright, now that we have covered the first 3 steps, let's get to the last one, getting the code changes approved and merged into a repository. This step is usually the part where you have to interact with code reviews and version control systems, 2 topics that I've actually covered in prior videos in this series. Therefore, I will refer you to those videos for more examples. However, there is one set of tools in this step of the software development cycle that is worth bringing up, and that is linters and auto formatters. These tools will detect stylistic and functional issues that are easy to fix, and will usually fix them for you. This helps avoid having the code reviews get polluted with issues that can obscure more serious issues in your code. Examples of such tools are Pylint and ClankTidy. Anyway, at this point, we have talked about each step in the software development cycle, so it's a good time to move on to discuss tools that are used in higher level software engineering tasks. When it comes to software engineering, actually writing code is just one part of your job, and typically it does not take the majority of your time within that role. The other tasks that you often have to deal with are ensuring the quality of your software, packaging and deploying your software, and finally coordinating work between teams and communicating with stakeholders. Believe it or not, there are many tools involved in each of these tasks that I want to bring up to your attention. So let's go through each part of the software engineering job and discuss some of the tools that are used to accomplish them. One thing of note is that I will go a bit faster through the tools in the interest of time. When you build large-scale software, ensuring the quality of software becomes a rather challenging task. There are build systems, testing infrastructure, monitoring systems, dashboards, and automation systems involved in making sure that your software quality remains high. Also, side note, but I have a separate video in this series on build systems. Anyway, let's break down each thing that I've mentioned here in a bit more detail. First are build systems, and at a high level, these systems allow you to compile, put together, and package your software. There are many build systems that you may encounter, such as GNU-Make, Bazel, Ninja, and Gradle. Let's talk about testing infrastructure next. As I mentioned, in the aforementioned video on testing and build systems, there is a testing hierarchy, each level enabling you to test your software at higher and higher levels of abstraction. The number of testing frameworks out there is actually eye-watering, but some of the more famous ones are JUnit, Mocha, Selenium, and GoTest. Now that we have talked about both testing and build systems, the next piece worth discussing is build monitoring infrastructure. This infrastructure provides a set of tools that help you see how the builds are going, where they are failing, what tests are failing, and helps with figuring out why tests are failing. Some monitoring tools include Grafana and Prometheus. Now, not all companies will use specialized build monitoring tools, but no matter what, some form of dashboards will be used. These dashboards are typically custom and purpose-built. Some uses of dashboards are to view package test pass rates over time, number of active and reported defects in software, and whatever else you may find useful. The last thing that I would like to mention is that a lot of the work in software engineering gets automated, so of course there are entire automation frameworks out there. These frameworks allow you to do a predetermined set of steps automatically for you. Examples of such automation frameworks are Jenkins, Ansible, Travis CI, and Circle CI. Now that you are sure about the quality of your software, you're probably looking to get it deployed. This is where you start to encounter the many tools surrounding packaging, distributing, and deploying software. This area is actually quite complicated, and unless you're working for a startup or on a team specifically dealing with this, you probably won't need to worry about it. Nevertheless, it is useful to know what actually happens to software once you write it. The first concept that is worth discussing is the packaging of software. One way to package your software is to just put everything together into a single coherent binary or executable. That, however, is a real pain to deal with, as you do not know what setup your customer will have. Therefore, there is this tool called Docker, which allows you to control that setup. Essentially, a Docker container is a virtualized runtime environment that is very much akin to a lightweight virtual machine that holds everything that is needed to actually run your software. Packaging code in a Docker container is an extremely common way to handle both software packaging and distribution nowadays. Anyway, in order to distribute your Docker containers or binary executable, you typically upload them to Docker registries, which is kind of like a code repository management service, but for Docker containers. Once there, a customer can download your executable and run it. However, a lot of software is actually automatically distributed by deployment systems. One such common deployment system is called Kubernetes. Kubernetes is essentially software that allows you to deploy, scale, and manage containerized applications. It's a really neat piece of software that allows programmatic scaling and management of your software deployment. Now, since Kubernetes is just the infrastructure software, there are actually a lot of tools that are made to help you manage your Kubernetes clusters. These tools include Helm, Argo CD, Tekton, and many others. As an example, I worked on the team at Google that developed Google Protspec and Annealing, which is a Google internal tool to manage deployment of code. Either way, enough about that. As you know, Rome was not built in a day, and it sure as hell wasn't built by just a single person. Just like Rome, building big software requires a lot of time, and many software engineers working on the software all together. This introduces a lot of challenges regarding work coordination and communication. Believe it or not, there are many tools that try to help with coordinating work and facilitate effective communication between teams. As you well know, one important part of problem solving is breaking the problem down into smaller pieces that are easier to deal with. The same applies to very large projects. A massive multi-year project is broken down into smaller chunks. These chunks are often broken down further into so-called tickets, and each ticket is assigned to an individual developer. Each ticket represents some work that needs to be done, and finished tickets represent complete work. There are tools that help software engineering teams manage all these tickets, with famous examples being Jira, Asana, and Trello. Now that you understand how work is tracked and assigned, how do developers pass around information about the design of software, both in terms of UI and in terms of the architecture and structure of software? The answer is also with specialized tools. For UI diagrams and mockups, the common tools are Figma and Adobe XD. For the structure and architecture of code, the more common tools are Lucidchart, Draw.io, and Microsoft Visio. However, more often than not, just a simple flowchart will not cut it for the more involved features, and this is where Google Docs, Microsoft Word, and Notion come in. Lastly, when it comes to end documentation, there are many tools that help you with generating easy-to-read and navigate docs. These docs can be both generated from the code and written externally. For docs generated from code, there are tools like JavaDocs, Doxygen, and Sphinx. For externally written docs, there are Read the Docs, MKDocs, and Confluence. Now, let's say that just communicating through documents, comments on tickets, and diagrams is not cutting it. What other options do you have? Well, at this point, there are actual communication platforms that usually have voice calling and text chat, such as Microsoft Teams, Slack, Google Meet along with Google Chat, and even Zoom. At this point, I think that I managed to cover everything that I wanted to discuss regarding tools. So let's move on to the next section of the video where I can provide you with some advice on how to use the tools at your disposal at work. Alright, now that I'm done with dumping an insane amount of information on you, we can take a breath and slow down. From now on, the information will not be technical in nature, but rather advice on what to be aware of, what to focus on in terms of self-improvement, and finally some general advice about the tooling at your disposal. The first piece of advice I will give you is to go to knowhello.net and read the entire page. You should do that right after this video, as this is an incredibly important resource that is actually very short. In essence, it motivates the need for not starting an instant message with just a hello, but rather asking your question in full as your first message. Actually, this is really useful advice in a different way. It forces you to put down your question in full up front. Just phrasing the question that way can actually make you come up with a solution, just like talking to a rubber ducky does. The next piece of advice is to get good at Googling things. There's a common joke in programmer circles that as you gain seniority, your Google queries get shorter and shorter. Thing is, it's not much of a joke, as with experience you realize that putting how to use a namespace in C++ into the search bar yields the exact same results as C++ namespace. However, knowing how to Google things effectively is not just useful in development efforts, it helps you find information that you care about very quickly. As an example, if you're a student, just looking up the name of a textbook in Google is probably not what you want. Looking it up and adding plus file type :PDF at the end, however, is. Anyway, with search engines out of the way, as you start a new job as a software engineer, you should really focus on building up a mental map of all the tools that you have at your disposal. Actually sitting down with some other engineer that has some work experience at the company and asking them about all the tools they got is a very good idea. Feel free to use the earlier parts of the video to ask which tools are used in each step of the software production cycle, and what tools are used for the rest of your job responsibilities. I'm sure that your new coworkers will find this curiosity a rather positive trait. Next, let's talk about debuggers. There is this thing that I have discovered while TAing students in university. Many students simply refuse to learn how to use a proper debugger and instead prefer to do what many call printf debugging, where you attempt to debug a program by sprinkling in print statements saying something like "got here." Thing is, debuggers are incredibly powerful, and you should take the time to learn how to use them as soon as you have the reason to think about a debugger. After a relatively small time investment in learning how to use it, your productivity will increase by a large amount. I can't imagine writing Python code without using PDB anymore. That's how important it is for me. The last piece of advice I have for you is to actually not stress yourself out about the volume of tools that exist out there. Here's the thing, I've mentioned a very large number of tools in this video, and I've personally often used only one or maybe two in each category. You also do not need to know about all the tools that exist out there right away. You will pick up whatever you need and find useful over time. Additionally, you really do not need to be an expert in every tool that you use. I certainly am not an expert even with the tools that I use every day. Just spend some time occasionally looking up how to improve your workflow and you will be okay. Anyway, that's about all the advice I wanted to share with you today, so let's wrap up the video. In this video, you have gotten a high-level overview of what tools are involved in the software engineering profession, both from the low level of actually writing code and all the way to the more abstract responsibilities of a software engineer, such as ensuring the quality of your code and communicating information to others about your code. While a lot of the information I have tried sharing with you here may seem a bit too abstract if you're very new and have never worked in industry, it should still serve as good context for what the tools involved in making software are and where they may be encountered. Either way, I really hope that this video was helpful and interesting for you. Feel free to check out this playlist here to watch all the videos I have on the topic of applied software engineering, especially if you're watching this in the future when I have already uploaded the whole series. Also, feel free to ask questions if you have any. I try to respond to all the comments I get, and I have made a few videos based on viewer requests so far. Anyway, thank you for your time, bye.